Okay, so what are we up to today? Well, last time we began our introduction to Z-transforms. The more broadly applicable transform we said was going to be just as good as the DTFT, only better. It would have certain capabilities that the DTFT didn't have, namely that it could be used on a broader range of signals because we had this added converging factor that we were adding in with the Z-transform that could take even diverging functions and still force them to form a converging series that would have a closed form solution. And so our Z-transform will cover a broader range of signals. And we promise that it would also have some unique properties that would enable us to go beyond the capability of DTFTs. We could do more than just finding frequency responses and how systems would respond to sinusoidal signals or even zero state responses to arbitrary signals by performing convolution with a simpler set of mathematics. We're going to have all those capabilities that we did with DTFT, but now we're also going to have the ability to use them with a broader range of signals and also be able to do some of the things that we couldn't do with DTFT. Most importantly, finding complete solutions, getting all the capability that we had in our time domain methods, particularly solving difference equations, having a better way to get at those same answers, including not just zero state responses, but zero input responses. That's the goal. That's why we're here. We got as far last time as going through the definitions of the Z-transform and some of the nomenclature and things that go with it, the region of convergence, what that looks like, how that's different for causal and non-causal signals, when those series will converge and where they won't. And today what we want to do is look at a simpler way of actually computing the Z-transform, particularly the forward transform, where we don't want to always drag out the defining summation equation whenever we want to do a Z-transform. Because again, the motivation here is that we want to use this as our primary tool for system analysis. And to do so, we're going to try to take complicated problems like solving difference equations or performing convolutions and move them somewhere where mathematically they're simpler. That's all well and good as long as if we're going to use transforms for that movement process, the process of taking a transform can't be adding so much additional work, so much additional mathematics that it makes going into the transform domain and coming back out not worth it anymore. And so our primary method of doing Z-transforms and inverse transforms for that matter will be using lookup tables. A set of tables, actually a pair of tables, the forward and inverse transform tables and the properties tables. So we'll get a little practice in how we do it that way. And then we're going to focus on the implications of one of the properties of the Z-transform, and that is namely the convolution property that gives rise to describing the behavior of the system in the Z domain, in the Z-transform world, with a particular function, the function we'll call h of z, or the transfer function. We'll relate that transfer function to poles and zeros, and those poles and zero locations to things that have relevance to the time domain response of our systems, the stability, natural responses, issues like that. So we're going to be doing things that will sound familiar, feel a little familiar, because the Z-transforms are the discrete time parallel to the Laplace transform in continuous time domain. So a lot of the same topics, a lot of the same issues that we're going to be talking about in the context of Z-transforms, you've already gone through in the form of Laplace transforms. We just need to rejigger them a little bit for this discrete time domain. So that's what we'll be up to. That will get us the foundation that we need to come back next time and start looking at some of the analytical techniques that we can actually carry out with Z-transforms. So returning to how we are going to compute the transform, predominantly the forward transform, but in some cases also the inverse transform. We can always do that with the defining summations. And well, so far we've only really talked about the forward transform, which has this particular summation, the sum of x of n, z to the minus n over all n for the two-sided Z-transform. And that's what we applied last time when we were trying to derive what the Z-transform and regions of convergence were for some basic function. What we want to do now is do that more simply with these pair of tables, with the transform pair table and the properties table so that we can directly get from the time domain to the Z domain much more quickly. And so it's these tables that we're going to want to have handy for us anytime we do need to take a Z transform, transform pair tables that have time domain functions and their Z transforms and information on the regions of convergence that result from those transforms. And then the properties table, which tells us if we can't find the exact signal we're looking for here in this particular lookup table, well, perhaps we're working with a signal that has some signal operation applied to it, like it has a time shift or a time reversal or a time compression or expansion, or it's multiplied by n, or it's multiplied by alpha to the n. Well, that's where the properties table comes in and tells us how do you take the basic transform for x of n and its transform x of z and adjust it for the case where you have a time shift, for example, or time reversal, or perhaps if you're working with an anti-causal signal, if you're applying some scaling, some exponential scaling to a time function, if you're multiplying it by n, if you're modulating it with a cosine or sine, and ultimately if you're working a convolution problem with it. And so this table tells us how do we modify the basic x of z, the basic transform function for the unoperated on signal, the x of n, and what substitutions, what changes, what operations do we have to do to the transform to adapt it to this particular situation? Like if we have a time delay, we take whatever x of n was, whatever that signal was, if we can find its Z transform in the lookup table, we take that transform and multiply it by Z minus capital N, where capital N is the time delay. If we happen to be reversing the time direction of our signal, we invert the Z variable. So we take our x of Z, everywhere there's a Z in that equation, we replace it with 1 over Z and simplify it. Notice that also inverts the region of convergence when we do that as well, which makes sense. As we saw last time, if we have a causal signal, its region of convergence starts at some inner radius and goes outward. If we flip it around and make it go the other direction, well, then it's going to have an inward will be part of the region of convergence. So that all jives with what we've seen last time. Time scaling, multiplying by a alpha to the n factor, means we take our Z variable and replace it with Z over alpha. Multiplying by our index variable n means we actually have to take a derivative with respect to Z of our Z transform and multiply it by minus Z, and so on. We can see if we have any of these operations done to our time domain signals, how we adapt the Z transform. And of course, our friend convolution, the one that we're really happy about, that says we have the same property with Z transforms that we had with DTFTs, thank goodness, because that says we don't have to do time domain convolution the hard way with lots of computations. We can actually replace that cumbersome convolution operation with simple multiplication of Z transforms. Well, let's look at some very simplified cases of how we apply these tables. Let you get the hang of it, then we'll try a little more challenging example. First, the very simplest Z transform, which we could have actually arrived at using our defining definition rather quickly, but just as an example here of the tables and properties, if we wanted to find the Z transform of a unit sample sequence, that's that 1, 1 at n equals 0 and 0 elsewhere. Well, simply looking up in the table, we would see that delta sub n's Z transform is a 1, which is a rather interesting result. It's the same value for all Z, kind of the opposite of the time domain function. It only has 1, 1 for a singular value of n. Turns out the region of convergence for this Z transform happens to be all Z. More interestingly is what if we want to know what's the Z transform of a shifted delta, maybe shifted by one position. That's not one that's necessarily in our lookup table, at least not the direct lookup table for signals in their transform pair. For that, we would take our known transform, delta sub n transforms to 1, and apply the shifting property that says if you know the Z transform of the unshifted function, which in our case is a 1, we're going to take that function and to see what the result of the Z transform is for the shifted version, we just take that transform, multiply it by Z to the minus capital N, where that's the delay. For us, that would be taking the known Z transform of delta sub n and multiplying it by Z to the minus 1, or simply Z to the minus 1. Had we known about those two transforms and that property, we could have saved ourselves a lot of time last time when we were trying to determine using the definition only of the Z transform for this particular function, which had 3 delta functions with different shifts, happened to be the unit sample response for an FIR filter. There was a minus 1/2 delta of n plus 1 delta of n minus 1 minus 1/2 delta of n minus 2. We went through this with the defining definition summation. It was a sum over all n of h of n z to the minus n. We weren't deterred by the fact that this is an infinite sum because there were only 3 non-zero values of h of n. So we only had 3 terms from this summation to work through. And we found that the Z transform happened to be minus 1/2 plus 1 z to the minus 1 minus 1/2 z to the minus 2. Now knowing about the properties of the tables and knowing that the Z transform is a linear transformation, which means it obeys additivity and it obeys homogeneity. So with that in mind and knowing the shift property that we just looked up in the table, this transformation can be carried out even more simply than it was with using the definition. Namely, because Z transform is a linear operation, if I have 3 different additive functions I'm going to transform, I can transform them individually and add their transforms. That was the additivity property. And if we know the transform of a delta sub n, we know the transform of minus 1/2 delta sub n because it's a homogeneous transform. If we multiply the time function by something, the transform is also multiplied by the same function. So right off the bat, we know that the Z transform of this combination is going to be minus 1/2 times the Z transform of this, plus 1 times the Z transform of that, minus 1/2 times the Z transform of that, again, because we have a linear transform. And the Z transform of delta sub n, we just looked up, that's simply 1. The Z transform of a delta sub n minus 1, we know from the shift property, that's just the Z transform of delta n times Z to the minus 1. And likewise, we know the Z transform of delta n minus 2 is just the Z transform of the basic function delta sub n multiplied by Z to the minus 2 for the time shift. And the delta sub n, we know its Z transform is a 1, so we just substitute that in and arrived right away at the same place we did with the defining definition. Good news there. Didn't want to get a different answer. Now that's all very straightforward with our simple delta functions. What about something more interesting like causal exponential, alpha to the n u of n, and typically alpha is going to be a value less than 1 if we have a converging function. Well, again, last time we rather laboriously went through the analytical solution of that summation. Just turned out it gave us a form that did have a finite known sum that we could look up that under certain conditions, which gave rise to our region of convergence, that it's the answer we're after today. We determined mathematically that the Z transform was Z over Z minus A, and the region of convergence, the magnitude of Z had to be less than alpha. Well, we could have arrived at that with our tables much more simply. In fact, this particular function is one we're going to use quite a lot. It has its own entry already in the direct transform table. Alpha to the n u of n, there it is just Z over Z minus alpha with its region of convergence. More interestingly, let's challenge ourselves by multiplying that by n. And okay, well, if you look at the table, there is this entry is in the table too, but let's pretend it's not. And so if I didn't know that it was already in there, I can actually use the properties to arrive at this same place because we know the transform for alpha to the n u of n. And there is a property that tells us what to do if we know the transform for some function, and we want to know what the transform of n times that function is, well, let's apply that and see how to get around to the same answer. The property says to take the Z transform for alpha to the n u of n, take its derivative with respect to z. That would be taking the derivative of this with respect to z, and then multiplying that by minus z. Okay, so that's what we want to carry out. We want to take the minus z times the derivative with respect to z of the Z transform of our basic function, alpha to the n u of n, which we look up on our table and see that's just z over z minus a. And then hopefully we will recall our first year calculus and can do a derivative of a quotient with respect to z, which is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. And in the numerator, we have a 1z and a minus 1z that'll cancel out. And we have a negative signs on the inside and outside that will also cancel, and we'll arrive at the exact same place we did that the lookup table was telling us. So just to illustrate that, while we had that actual answer waiting for us in the table, if we have another case where that's not so, we can apply this n times property to tell us how to deal with this particular situation and take a simpler function's Z transform and find the Z transform of something more complicated. Now, we're moving through this really quickly, mostly because conceptually it's very similar to Laplace transforms. You've been doing these kind of forward and inverse transforms for several different flavors of transforms so far. So I'm going to move rather rapidly, but please do ask questions. Please do stop me if there's things that you're seeing that don't make sense. If there's steps that you're not seeing the connections on, please do feel free to stop, because again, if you're not seeing it, very likely that there's several other folks who are also struggling with it, and they'd love for you to ask that question too. So here's one for you to give a try to, and this one's not in the table, not quite so easily. If we had a function for n u of n minus 2, and I ask you, what's the Z transform of that, knowing that we have these transform pairs and properties available to us, give that one a try and go ahead and work that in your notes for a minute or two and see if you can't come up with what the Z transform is. And we'll talk about that in a minute. So go ahead and give that a try. I will warn you, there is a trap you can fall into. Be careful about this one. I would suggest taking this in a couple of different steps. First of all, we would want to know what's the Z transform for U of n. And well, if you have a more complete table than this, there actually is an entry in a lot of tables for U of n that tells you it's Z over Z minus 1. Not knowing that, though, if you only had these available, if we're clever about this, we can actually adapt this first one, the alpha to the n U of n, into finding the transform for U of n just by assigning alpha the value of 1. 1 to the n is just 1. And in that case, we would replace alpha with 1 and have Z over Z minus 1. That gets us U of n. We want U of n minus 2. Well, as with that previous example, that's a time shift. And so that says just take our U of n Z transform, which we just found, Z over Z minus 1, and multiply it by the time shift factor Z to the minus 2, because we're using a minus 2 exponent because we have a minus 2 shift here. And that would give us a 1 over Z times Z minus 1 in the denominator there. And then finally, we've got U of n minus 1. Now we need 4n times that. Well, the 4 is just a multiplier. So linearity says we just multiply our transform for n U of n minus 2 times 4. And for the n, we'll use that n times property, just like we did in the prior example, that says we're going to take the Z transform from this second part, the U of n minus 2 part, take its Z transform, take the derivative with respect to Z, multiply by minus Z, and again have the 4 as a multiplier out in front because of the 4 coefficient in front of our x sub n. All right, that's the hardest part. We need to somehow do a derivative of this 1 over Z times the quantity Z minus 1, which is the same as 1 over Z squared minus Z. And again, working that through with our quotient rule and doing some algebraic simplification leads us to the final answer, 4 times the quantity 2Z minus 1 over Z times Z minus 1 quantity squared. A little more complicated of a Z transform. Now, the trap you can fall into is there's a lovely entry here for nu of n, and you'd love to just multiply that by 4 and shift it by 2. But the issue is, remember when we do a time shift, this shift must apply to all the arguments in the function. So if I were going to apply this time shift, I would need u of n minus 2. I'd also need this n to be n minus 2, as we saw when we applied time shifting examples in the DTFT version. And so while that would have led to a quicker answer, it wouldn't have been a correct answer. Everybody okay with that example? Any questions? Anything that came up for you when you tried that you're not seeing right now? Okay, hearing none, let's move on. There's several other properties, we could spend a whole nother class talking about using these in detail. Let me just briefly mention them and prepare us to use them when they come up in the future. We won't be doing a lot with time reversal, particularly when we start employing the one-sided Z transform. That will be one that we actually don't want to use once we're in that regime. And we're not going to work with a lot of anti-causal signals. We're typically working in our system analysis with causal systems, that meaning they have causal unit sample responses, and we apply causal signals to them. So we'll have less occasion to use and worry about anti-causal signals and systems, although they will exist. For scaling, though, we may run into this, have exponential scaling of a function. We definitely have seen the times n used a couple times. It's possible we might have a signal that's modulated by a cosine or sine. And these transform properties tell us how to adapt the Z transform in that case. We have to do an extensive substitution, then replacing all the Z's in our Z transform x of Z with a Z e to the j omega, where omega comes from the radian frequency of our modulating cosine. And again, what we're going to do is make a copy that has that substitution, add it to another copy that has a substitution with the opposite phase, Z e to the minus j omega, and multiply each of those by 1/2, effectively shifting its baseband up to some other frequency. Whether we do it with the cosine or the sine, the only difference with the sine is that we have this extra j factor out in front and a minus sign on the negative phase part. The most important of our properties, though, for the Z transform is that it retains the convolution property, that when we transform a convolution of two signals in the time domain, it turns into a simple multiplication in the complex Z domain. The regions of convergence of that multiplication, though, become the intersection of the regions of convergence of the two signals that we were taking the transforms of when we were trying to convolve them. And when we put this in the context of system analysis, we use convolution to take the input signal x of n and convolve it with the unit sample response h of n to determine the output of a system y of n. That translates in the Z domain to multiplying the Z transform of x of n by the Z transform of the unit sample response, this thing we're going to call h of z, that we'll call the transfer function of the system. And so with that multiplication, we'll determine the Z transform of the output signal. This indicates to us that this h of z thing is the part of the convolution process in the time domain. It's the unit sample response. In the Z domain, this h of z function is the part that describes the system behavior that has to hold within it all the knowledge and all the mathematical modification that's going to instill in that input signal the response of the system to that signal. And so that's where our dynamic behavior of our system's description is going to be held when we're in the Z-transform domain. So when we get to doing system analysis, particularly zero state response analysis, as we did with DTFTs, so we can do with Z-transforms. We can find the output signal for a given input signal. If our system started out relaxed, instead of doing that by convolution in the time domain, that convolution property says we can pick up that whole problem, Z-transform it into the Z domain, and that convolution operation comes across as multiplication of transforms as opposed to convolution of signals. When we do a convolution to find a zero state response this way, what we end up with is not the real answer we're looking for, but the Z transform of the output signal. And so there is implicitly another step that has to be completed to take the product of h of z and x of z, which is the Z transform of the output signal, and go through an inverse Z transform using tables, probably using partial fraction expansion, and another set of tables of the partial fraction terms and what they translate into in the time domain. Also tells us that this system function h of z is related to the unit sample response, just as the frequency response, the DTFT frequency response, h of f, was the discrete time Fourier transform of the unit sample response. And that's what gave us the Fourier domain description of the system's behavior and how it was going to modify signals of different frequency. So the Z transform of h of n, the unit sample response, will give us the transfer function h of z, which tells us how the system will respond to signals that have different content, different poles, different values of z. And so the rest of today, we want to focus on that system behavior descriptor, h of z, the thing we're going to call a transfer function, and the other related descriptions of the Z domain behavior descriptors, the pole zeros, what those are, how they relate to the time response of the system, and setting us up for next time we come back and really closely connect them to the frequency response of the system. So this transfer function thing, this is the h of z thing. This is going to be our way to look at how systems behave in the Z domain. Based on our convolution property, we said that h of z is the ratio of the Z transform of the output signal to the Z transform of the input signal. That's what the convolution property suggested. And once we have this h of z function, what we're looking at is the Z transform way of describing the system's dynamic behavior. It contains within it all the same information that the difference equation contains. And in fact, it also contains basically all the essence of the unit sample response because it's the transform of the unit sample response. And so it has direct ties back to our two time domain system describers, the difference equation and the unit sample response. In the case of the unit sample response, well, h of z is by definition the Z transform of the unit sample response. So whether it's with the lookup tables or using the transform definition, we can take that time domain unit sample response, whether our system is FIR or IIR, and come up with its transfer function. More likely though, because oftentimes, unless we have an FIR system, we're less likely to have the unit sample response readily available to us. We're more likely to have the difference equation. And so what we want to be able to do is to derive this transfer function directly from the difference equation. And guess what? We can do it the same way we found the frequency response directly from the difference equation when we were looking at DTFTs. Namely, we're going to take the difference equation of our system, which for the system shown here, we could derive pretty quickly. This output's a recursive system, but easy to recover the difference equation from the block diagram. This one happens to be y of n minus 1/2 y of n minus 1 equals x of n plus x of n minus 2. We have a 2-sample delay here. And we're going to follow the same outline that we did with DTFTs to derive the frequency response from the difference equation. Namely, we're going to apply, in this case, the Z-transform one term at a time and take those Z-transforms and rearrange them to create the ratio that we need for the transfer function. So we take one term at a time, take y of n, Z-transform it to y of z, take the minus 1/2 y of n minus 1, Z-transform it. Well, that'd be minus 1/2 times y of z with the time shift property multiplied by z to the minus 1. And on the x side, we have x of n's Z-transform x of z, and x of n minus 2 Z-transform is just x of n with a time shift of minus 2. Now we can factor out a y of z on the left and a x of z on the right, and then create the ratio for the transfer function that's y of z over x of z. And from that previous equation, that ratio is equal to 1 plus z to the minus 2 divided by 1 minus 1/2 z to the minus 1. We have the transfer function of our system from the difference equation. Now, it's typical of transfer functions that we prefer them to not have negative powers of z, predominantly because we're going to want to factor them. And so I'm going to multiply this particular one to convert it to positive powers of z. I've got a z to the minus 2 in the numerator, so let's multiply the numerator and denominator by z squared. That'll leave me a z squared plus 1 in the numerator and a z squared minus 1/2 z in the denominator. And that'll be our h of z that we'll take forward for some examples here. Everybody good with how we did that? It's, again, exactly analogous to how we did it with DTFTs, just we're using Z-transforms this time. But notice how simple that is to get right from the difference equation right to h of z. Okay, so what are we going to do with this h of z thing? Well, before we go any further, I want to point out that that process we went through is going to go exactly the same way no matter what our system is like. Because if we have a linear time invariant system, we said it's described by a very particular kind of difference equation, a linear constant coefficient difference equation that we could put in this standardized form with y's on one side, x's on the others, a coefficients with the y terms, b coefficients with the x terms. And when we take this kind of a generalized difference equation through that same process to derive the transfer function, same kinds of things are going to happen. We're going to Z-transform. We're going to have a whole bunch of y of z's on the one side, a whole bunch of x of z's on the other side that we can factor out. And we're always going to be left with the same appearing kinds of functions. Y of z times some descending power of z polynomial with a coefficients, x of z with some descending power of z polynomial with the b coefficients. And when we create the h of z ratio, it will always, always, always be identically structured. b0 plus b1 z to the minus 1 plus b2 z to the minus 2, and so on, however many terms we have from the right side of the difference equation, divided by 1 plus a1 z to the minus 1 plus a2 z to the minus 2 plus however many terms we have from the left side of the equation. Always in the same form, always two descending polynomials in z, with the b coefficients on top, the a coefficients on the bottom. Maybe with different polynomial orders on the top and bottom, that's okay. If we want to put this in a factorable form, we'll multiply top and bottom by z to some power, and again end up with a polynomial in z in the numerator and some polynomial in z in the denominator, hopefully that are factorable. And so we'll have a collection of factors in the numerator, a collection of factors in the denominator. And we're going to call the roots of the polynomial in the numerator, these z1, this z2, and however many of them we have, we're going to call those the zeros of h of z. Why do we call them zeros? Because if I assign z in h of z any one of these values, z1 or z2 or any ones that are in this numerator, one of these terms is going to be 0, which makes the whole numerator 0. And unless that same term appears in the denominator, in which case they would have canceled, we'll get a non-zero value in the denominator. And so h of z will always take on the value of 0 when we choose z to be one of these 0 values from the numerator polynomial. So clever name. These are the zeros of h of z because they're the values of z that make h of z go to 0. Likewise, the roots of the denominator polynomial in z, p1, p2, however many of those we have, those are the values of z variable that will drop a 0 into the denominator, which makes h of z want to go to infinity. And so they're values of z where we'll have actually singularities in our h of z function. It's going to want to go off to infinity in the vicinity of those z values. Thus the name poles, like tall tent poles trying to push off to infinity. So if we use the example that we derived from our block diagram and difference equation, here's our transfer function h of z we just derived. If we factored this, we did put it in positive z polynomial form. So we factor it. These factors are z plus j and z minus j for zeros. The poles factor to z equals 0 and z equals plus 1/2. And so we have that factored. Now, in its factored form like this, knowing its poles and zeros, we have an alternative way to describe h of z graphically. That's with a pole zero diagram, a graphical representation of the transfer function. This is where we reintroduce again our z-plane like we did last time, an Argand diagram, a complex variable plane here. It has a real axis on the horizontal and imaginary axis in the vertical direction. At any point on this grid represents one particular complex value of the variable z in our transform h of z. We keep track of the unit circle, which we'll see shortly why it's a really critical place in the z domain. And on a pole zero diagram, we're going to use zeros to show the locations, the z values that are zeros are our transfer function. In our case, we have zeros at plus and minus j. So I'll draw a 0 at z equals plus j in our pole zero diagram, and another one at minus j. Our function have poles at z equals 0 and z equals plus 1/2, and I use x's on a pole zero diagram to show where the poles of the function are. And now with this diagram, I have completely specified for you h of z for everything that you need to know to reconstruct h of z, with one small exception. If there's a numeric constant out in front, a scale factor, I don't see that in here. I would need one other piece of information, like the value of h of z at some particular z value, in order to solve for that gain factor. But otherwise, I have all the structural details of my h of z right here in this diagram with a couple of x's and o's. Very compact, very convenient way to graphically represent a transfer function. Now, you might ask, okay, that's where the poles and zeros are, but where's h of z? Well, if I was going to plot h of z, number one, first issue, it's complex valued, so it has a magnitude and phase. So, all right, let's say we want to plot the magnitude of h of z versus z. Well, my usual 2 dimensions of a plot are taken up just by my complex z values, so it's not going to look like my frequency response plots do. It's going to have to be another dimension coming out of the board for my height of my h of z magnitude. And it's going to have different heights depending on the magnitude of h of z and how that changes with z value. In fact, this particular function, if I were to plot that surface and how its contour changes with z, it would look like this, where my z-plane is down here with my zeros and my poles, and the magnitude of my h of z function is plotted at its height is the magnitude of h of z above every possible value of z that I might plug in here. Now, how does one kind of arrive at a visualization of what this might look like? Well, there's a analogy that we like to use to help you visualize that, and that is, think of the magnitude of the transfer function h of z plotted above the z-plane like that. So the ground level is your z-plane, the real and imaginary axis. And the magnitude is going to be a rubber sheet, a very stretchy rubber sheet that sits above that plane. And you're going to tack that rubber sheet down anywhere, any z location that has a 0, you're going to tack that down to the ground. And then any place where you have a pole, you're going to stretch that sheet up to infinity with a very tall tent pole. And then this infinitely stretchable rubber sheet is going to try to fit the contour in between and again the shape that it takes to describe h of z. So anywhere there's a 0, it's going to get pulled down to 0 at plus and minus j. Anywhere there's a pole, it's getting pushed off to infinity. And where it goes at the edges, you have to look at what does h of z do as z goes to infinity. And if in this case you have the same order polynomial in the numerator and denominator, as z gets huge, that function will settle out at 1. And so we see the edges of the rubber sheet contour want to level off at 1 at infinity, and held in place there and stretched and pushed by our poles and our zeros, we see its contour, where again what this represents is what's the value of the magnitude of h of z for any particular z value. I find the z value I want to evaluate it at, go up and see how high is the rubber sheet above me there, check its altitude, its height there. That's the magnitude of h at that particular z value. Here's a more complicated system that has, well, looks like it has 4 poles and 4 zeros, not 2 of each. And if we wanted to draw the pole zero diagram for this, well, let's start here. We have a z squared, that's a 0, because it's in the numerator, at z equals 0. Now here we need to talk about how do I show on a pole zero diagram a multiplicity, a redundant pole or 0. Here I have the same 0 happening twice. The way we do that is use our polar 0 symbol, in this case a 0, and put next to it the multiplicity, the number of times that that 0 occurs in our transfer function, in this case twice. Another 0 at z equals plus j, the other one at z equals minus j, poles at z equals plus 1/2, z equals minus 1/3, and z equals minus 1 minus and plus j 1/2. And this would be a pole zero diagram of a system that, again, other than a numeric constant out in front, if I gave you this diagram, we could actually recover this h of z directly from it. Now, we'd like to also be able to ask other meaningful questions like, is this a stable system or not? And for that, we need to consider what the poles are telling us about this function. Starting with how poles relate to the region of convergence. And here's a thought question for you. If the poles of h of z are the values of z that make h of z go to infinity, do you think that a pole value of z would be allowed to be inside the region of convergence of h of z? Anybody? Does that make sense? Should the poles be inside the region of convergence?
No.
No. They're doing the exact opposite. They're forcing complete divergence. So no, poles cannot be in the region of convergence. So the region of convergence of our function is not allowed to include any poles. How about zeros? Are they going to be okay to live inside the region of convergence? Is that okay for the force things to zero?
Yes.
That's cool.
Yeah.
Okay. So here's our first rule. Poles cannot live inside the region of convergence of your function. Doesn't matter if it's causal, anti-causal. If it's got a pole, it can't be in the region of convergence. We looked last time at the directions of the region of convergence and how it was different for causal or right-sided signals versus anti-causal or left-sided signals. For causal signals, we said that the region of convergence starts at some radius and goes outward from there. Now, if I have a causal transfer function with a bunch of different poles, how are we going to determine where the region of convergence starts for this function? Well, if the region of convergence goes outward and is not allowed to include any poles, obviously, it can't start until that outermost pole, the one with the largest pole radius, the largest magnitude. It can start there, well, actually just a smidge beyond there, and then go out. It can't start here at A, can't start here at B, because then it would include C in the region of convergence. So the region of convergence for a causal signaler system has to start at the outermost pole, the largest radius pole, and move outward. Anti-causal or left-sided was the opposite. They had regions of convergence that went inward. Therefore, if we have multiple poles, now we have to choose the innermost pole to start that region of convergence, the one with the smallest radius, and then go inward from there. Because again, the poles cannot be inside the region of convergence. Turns out if you have two-sided functions that might have multiple poles, the region of convergence is going to be a donut squeezed between one pair of those two, but again, can't allow any poles inside that region of convergence. So that's regions of convergence. Now, how does pole locations affect system stability? Here's where we start making connections back to the time domain. Remember when we had solving difference equations, we said the way we tell a system if it's recursive, it would be stable if the roots of the characteristic equation had magnitudes that were less than 1. Well, what is the characteristic equation? Remember, we took the difference equation, we applied the delay operator to it, and that gave us the characteristic equation. But did you notice that what we did was take the Z transform of the left side of the equation when we applied that delay operator? All we were doing was taking the Z transform actually of the left side of the equation to create the characteristic equation. And then we were looking for, setting that equal to 0, looking for its roots. Guess what? Now that characteristic equation lives in the denominator of h of z. And oh, by the way, the roots of the denominator are the poles of h of z are the same thing as the roots of the characteristic equation. So all the things that we did with roots of the characteristic equation, we now do with poles. Make that equation in your mind. Poles equals roots of the characteristic equation. They are identical. So finding the roots of the characteristic equation is the same as finding the poles of h of z. If our stability criterion was the magnitude of the roots of the characteristic equation had to be less than 1, guess what? The poles of h of z have to have magnitudes less than 1. So they have to be somewhere in the z-plane inside of a radius of 1, which means all poles have to lie inside the unit circle if we have a causal system. So if we have a causal and right-sided system, and we need for the region of convergence to start at the outermost pole and go outward, and all the poles have to be inside the unit circle, that means it's guaranteed that the region of convergence includes the unit circle. And same way for an anti-causal system and two-sided systems, following the rules, we'll always place the unit circle inside the region of convergence. And so that is our generalized stability requirement for Z-transform systems, transfer functions. No matter if it's causal, anti-causal, one-sided, two-sided, doesn't matter. The region of convergence must include the unit circle. The poles have to be inside or outside the unit circle, depending on whether it's causal or anti-causal or not. However, the region of convergence, wherever it is, must include the unit circle for the system to be stable. And one last connection, then we'll let you go for today. If the poles of h of z are the roots of the denominator polynomial and therefore are the roots of the characteristic equation, they also determine, as the characteristic equation roots did, poles also determine the form of the natural response of the system. Remember, we had this table that related the kind of root of the characteristic equation we had to the form of the natural response. Now, change that roots of the characteristic equation to poles of h of z, and you have exactly the same thing. Depending on if those poles are real and distinct, repeated, complex, or complex and repeated, we get a different form for the time domain natural response of the system. So we now have all this collection of different system descriptions for our linear time invariant systems, to which we now add transfer functions and poles and zeros. And your job, my job, is to make sure that we can walk around this diagram, start anywhere, and derive any of the other functions. Start at the difference equation, find our way to frequency response, transfer functions, impulse responses. From a z-plane pole zero diagram, get back the transfer function. From there, get back the difference equation, and so on. We'll come back next time and practice a little bit of that, and then also look at what other applications we can make now solving problems with the Z-transform, working on things like zero state responses, frequency responses, steady state responses, therefore, to sinusoidal inputs, and then work our way to the holy grail we were after, which was the complete solution, a zero state response and zero input response for a system for a particular input with a set of initial conditions. That's what we're shooting for. That's what we'll come back and work on starting next time.